Now, our today's topic is energy in elastic material, and of course, the continuation of elasticity. Now, under it, we are going to discuss about tensile strain, tensile stress, Young modulus. Now, when we say tensile strain, we mean change in length per unit length. That is change in length over original length. The ratio of change in length to original length. Therefore, tensile strain is equal to change in length over original length, where change in length is same thing as extension. So from this, it shows that this strain vary directly with extension. Therefore, strain vary directly with extension. Now the next term is tensile stress, which is the ratio of force applied to area, that is force per unit area. Therefore, stress is equal to force over area. So from here, this one also shows that the stress vary directly with force. Therefore, stress vary with force. Now, this one, the unit of this one does not have unit, because this one is in meter, that is strain, does not have unit. Extension is in meter, length is also the meter, it will cancel each other. While this unit for stress is Newton per unit per meter square. Newton, the force is for Newton, area is meter square. To now give what? Newton per meter square. Now, don't forget, in our Hooke's law, the equation that we got through Hooke's law, we have force vary directly with extension. Now from here, if strain vary directly with extension and force also vary directly with extension, it means force vary directly with strain. Therefore, force vary directly with strain. Now, this one, if stress vary directly with force here, and that same force vary directly with strain, so this one shows that stress vary directly with strain. Then what will now be the constant of variation? Therefore, stress is equal to K strain, where this K is called Young modulus. Therefore, Young modulus is equal to stress over strain. Therefore, Young modulus is ratio of tensile stress to tensile strain. This is how to prove it. And what will now be the unit of Young modulus? Since this one does not have unit, so it will maintain the unit of stress, which is Newton per meter square. Now, let's go to the next one, which is energy in elastic material. Now, when you have an elastic material in our first topic, so this is our elastic material. So this is original length. This is original length of this shape. Now we believe that since we have not applied any force, the force on it, F naught, is equal to 0. F naught on that material is equal to 0. Therefore, if you now apply force to it, the length of it now is original length, that is N naught. By the time you apply load on it, let me raise it up. By the time you apply load on it, it will expand. If you now want to calculate energy in this material, so what you do, according to the definition, energy in elastic material can be defined as product of average force and extension. When we say average force, it means F naught. Average force is equal to F naught plus F over 2. Where this F naught is the force when there was no any load on it, and that will become what? 0. Then the force applied now, we can easily get that force by calculating this mass and multiply it by what? By 10. That is mg. Therefore, this is average force. The energy on it will now be product of this one and extension. Therefore, energy in elastic material is equal to this one, F naught plus F, everything over 2 multiplied by extension, where this F naught is equal to 0. Therefore, energy is equal to F E over 2. Then, this is not only formula. We can still derive another formula from here. Because according to Hooke's law, our F is equal to KE. So we can remove this F and replace it with KE. Therefore, energy is equal to KE for this F multiplied by extension divided by 2. Therefore, energy in elastic material can also be calculated using KE squared over 2. Therefore, you can use this one or use this, depend on the question. So that is the end of the topic for today.